Hello, welcome back to our course on advanced quantum mechanics. Today we will find out, among other things, why it is that quantum mechanical predictions are probabilistic. So how far did we get so far? Remember, in the hierarchy of abstractions on the quantum mechanical side, we are now able to start with a Hamiltonian of the x hat and the p hat. And then we derive from the Hamiltonian what the equations of motion are. And we also have the canonical commutation relations and the hermiticity. So, starting from the Hamiltonian, we know how to derive the set of conditions that we have to fulfill, in particular, the differential equations of motion. We use Poisson brackets for that, and the Hamilton equations, Heisenberg equations, and all that. And from that, we have now managed to also calculate solutions to these differential equations and other conditions. And these solutions we found in the following form, namely as matrix-valued functions of time, p hat j of t, matrix valued functions of time. And then notice this means we also have, we also obtain automatically the matrix description of all other observables. So if f hat is some polynomial in the x hat and the p hat, for example, then we obtain that because, for example, if we choose f hat to be f hat of t, if we choose f hat of t to be, for example, the third component of the angular momentum, then what is this? Well, we can express it in terms of the position and the momentum. This is x2 of t, this is x1 of t, p2 of t minus x2, this is a 1 here, x2 of t, p hat 1 of t. And clearly we have L hat 3 of t because we know what x1 is as a matrix, assuming we have solved, we've done our job on finding the matrix representation of x hat, of the position and the momentum variables. Then clearly we also have any polynomial of that. We just need to multiply those matrices with each other to get the polynomial in question, such as the angular momentum. So having solved for the positions and the momenta as matrix-valued functions of time, we've really solved the entire problem here. Or have we? Well, not quite, because we still don't know yet how to make number predictions. So what we need to do is now find out how to get to number predictions. And for example, x bar of t, p bar, well, that could be an index, of course, p bar of t, the Hamiltonian of time, L bar I, the angular momentum of time, and really for any observable its prediction as a function of time. Remember that observables are these expressions in X and P, which have the property that if you take the Hermitian conjugate of it, so as far as a matrix is concerned, transposition and complex conjugation, they get itself again. That's F hat of X hat and P hat. Okay, so we need to find now a method for boiling down our solutions, in quotation mark, namely the matrix valued functions of time, into number valued functions of time, the actual predictions for the number valued outcome of a measurement of position, or a measurement of momentum, or a measurement of any other one of the observables that we can think of here. But how do we do this? After all, these X hat and P hat that we found are not just matrix valued, they are infinite by infinite matrix valued. So how to extract number valued things from, how to extract numbers from matrices? Let's be systematic. Let's be systematic for this step here from matrices to numbers. And the first observation we make here, the first consideration, the first hint for what we have to do is this. The prediction for an observable, which could be position, momentum, angular momentum, or whatever, must be independent of the choice of bases that we use. It must be independent of our choice of bases. Our choice of bases. You see, when we solved the equations of motion to obtain X hat of t and P hat of t for the examples that we consider, the free particle and the harmonic oscillator, we obtained matrix valued functions of time. And every matrix is at heart, fundamentally, every matrix is a linear map that you choose to represent in a basis. That same linear map you could describe in a different basis. So whatever matrix valued functions of time we found, we could always change bases in our vector space. Then these matrices would look different, but they would still obey the equations of motion, hermiticity, commutation relations, all of that, because we've just changed bases. It's still the same linear maps. Remember when we were at this point in the argument, 2 or 3 lectures ago, we said, in quantum mechanics, the X hat and the P hat have to be non-commutative, so they can't be number valued. Where could they take their numbers? Where could they take their values if not in numbers? And then we said, well, every object in mathematics can be described as a map, one way or the other. And there are nonlinear maps and linear maps. And then we said, fortunately, it suffices to consider linear maps. So we settled on linear maps, and indeed we were able to solve the conditions of quantum mechanics, commutation relations, equations of motion, with the X hat and the P hat being linear map valued. Concretely, we chose implicitly a basis and then found these linear maps as matrices. Matrices are linear maps of column vectors into column vectors. But we could choose any other basis in the same vector space and get a different matrix representation for the same linear map. Now, what we just wrote down here is a fundamental requirement, namely that the prediction, the number-valued prediction that we are going to make, must be independent of our choice of bases. This is simply saying that nature doesn't care about our choices, right? If I have a favorite basis that I want to work with, or I change my mind and choose another basis, nature cannot care about my choices of bases. So the predictions must be independent of the choice of basis that we use for our matrices. So that means, mathematically speaking, that f bar of t, whichever way we obtain it from f hat of t, it means that the f bar of t, our prediction, must be scalar. Must be scalar. But how do we obtain a scalar from a matrix? Well, the scalar product. For this, for obtaining, it's so difficult to write when I can't see what I'm doing. For obtaining a scalar from a matrix, we have the scalar product. That is what the scalar product is for. So, recall, given two vectors, let's call them psi and phi, in a basis. So we have psi given as psi1, psi2, psi3, dot, dot, dot. And similarly, we have that phi is given with phi1, phi2, dot, dot, dot. Given two vectors in a basis by giving their coefficients, and these coefficients could be any complex numbers, then, and this is just a matter of linear algebra, then we have that the sum over all I and j for infinite dimensional vector spaces, they would run from 1 to infinity, of psi star I, and then one of our matrices, f hat, of t with coefficients, matrix coefficients I and j, and then summed over j, is a scalar. And therefore, because it is scalar, it is basis independent. So the f hat of t could be x of t, x hat of t, it could be p hat of t, Hamiltonian as a function of t, etc. So is this the solution? Could it be that we now know how to take that step? In the hierarchy of abstraction of quantum mechanics, we go from the Hamiltonian to the equations of motion. We solve that with matrix-valued functions of time. And then we somehow come up with two vectors psi and phi, and we slap them left and right onto our matrices, evaluate that scalar product, and we get number predictions. And these number predictions are what is supposed to be measured then in an experiment. Right, so we take this matrix, apply it to this vector, we get a vector, and then we take the scalar product of that vector with the psi. So that would be the idea. But could this possibly be right? The answer is, well, is this correct. Correct. So do we have that f bar of t is, let's put a question mark over this, is simply psi, well, there are sums involved in this, is simply I, j, psi star I f hat of t I j phi j. Is that how we get predictions? The answer is no. And the reason why this cannot possibly be right is that these expressions, well, let me put it this way. Reason, in this case, the predictions, the number value predictions, f bar of t, would be complex numbers, not necessarily real. And that's a problem, because all measurement outcomes are real numbers. We've never measured a complex number. Sorry, we've never measured an imaginary number or a complex number that's not a real number. So we can't quite be right with this, right? If you look at this expression here for f bar, that expression has no reason to be real. Phi is a Cannon vector with complex coefficients. The f hat has complex coefficients. The psi has complex coefficients. Why on earth would the f bar come out real? It's generally complex and therefore ruled out as our predictions. So then what is it? How do we get from our matrices to number value predictions? We can fix this. Namely, assume we use only one vector psi. And we define f bar, the number value prediction, to be derived from the matrix valued solution of the equations of motion and the commutation relations, to be sum over the i's and the j's, and then psi star I, and then the f hat matrix, indices ij, and then the same vector here. And we can also write this as psi dagger f hat of t psi without using indices, right? Because after all, the whole thing is basis independent, so we can also write it in this more abstract form. So this will work. Why? Let's see. First of all, this is scalar. This f bar of t is scalar, and that's obvious because it's obtained by a scalar product, right? We apply a matrix onto a vector, namely the f hat on the psi, and that gives us a Cannon vector again. And then we take the scalar product of this vector with psi again. So that's a scalar product It's basis independent. And we have that f bar of t is now in all circumstances always real. Now let's prove that. Let's prove that f bar of t is real. Now we'll use that for any observable f hat, we have that f hat dagger is equal to f hat. This is by definition what a observable is. So we will use this. Now let's calculate. So we take f bar of t, so the number valued supposed prediction, and we take the complex conjugate of it. Now what is this? This then is the complex conjugate of sum over r and s of f bar of t. So this is psi star r, and then f of t rs, and psi s complex conjugate, right? This is equal to sum over r and s, and then we have psi r and f hat of t with coefficients rs, the matrix, the rs matrix element, and then we have to take the complex conjugate of it, because we're taking the complex conjugate of everything in that bracket, and these are all numbers in this bracket, right? These are the coefficients of a vector, these are the coefficients of a matrix, all these coefficients are numbers. And we just take the complex conjugate of that. And then here we have the psi star s. Okay, and we can write this now as the sum over r and s of psi star s. I'm just moving this around because these are numbers. I move this number to the left. And then we have here f hat of t. Sorry, this is SR. SR and psi r. And why do we have this? Well, recall that we have this hermeticity condition, which means that FSR is equal to what you get when you transpose and complex conjugate. So it's FRS star, right? This is the statement that f hat is equal to f hat dagger, because the dagger is complex conjugation and transposition. So this is what we used over here. And now we can see that this is equal to f bar of t. So therefore, we have that f bar of t star is equal to f bar of t, and therefore we have that f bar of t is an element of R, is real. Okay, so our number valued predictions, which we always will denote with a bar over the variable to distinguish from the f hat, which is the entire matrix, but f bar is just a scalar, it's just a number. that is definitely a good candidate for being the proper prediction. So how do we predict now? It's not just a candidate, it's actually the real deal. This is what it's going to be. So we obtain all predictions now. For example, we obtain a prediction for the position expectation for the position that it is given by sum over n and m of psi star n x hat of t n m psi m. It's very concrete, right? We pick some vector psi and then we use our solution x hat and we work out what this is. We get a real number. That's our prediction for the position as a function of time. And similarly, the p hat of t is equal to sum over n and m, psi star n, and then we have p hat, the p hat matrix that we calculate, and m, psi m. And you might think, okay, this is all boring, this is all easy, I know how this goes. And you might be annoyed because I haven't told you what on earth this psi vector is. We will get to this. We will arrive at it very systematically. So for example, for the energy, we of course also have this then, right, for the Hamiltonian, and for any other variable such as angular momentum as well. This is the procedure for calculating from the matrix valued solution what the number valued prediction is for all times. So this means we did it, right? Let me write this out. We did it. So we did what? Well, we went from the Hamiltonian, we calculated, we found out how to calculate the equations of motion, the canonical commutation relations, and the hermiticity conditions. From that, we encountered some methods for actually solving these equations to obtain x hat of t and the p hat of t, etc. And now we also know how how to obtain predictions for numbers. X bar I of t, p bar j of t. And here we just choose some vector psi for the purpose. And once we have chosen that vector psi, then we can make all those predictions. So, and I should add here f hat of t and f bar of t. So now we can predict everything. We can go all the way from setting up a system by defining its total energy, all the way down to the predictions of numbers for all sorts of measurements that we can imagine, for all sorts of observables. And we've also seen that the condition of hermiticity is really the correct one, because it was the condition of hermiticity that we imposed on what we call observables that saved the day when we wanted to get down to the predictions of real numbers, because it was the hermiticity condition that we used to guarantee that all of our predictions, all of the F bar, are real. But there is, of course, something amiss here. Namely, we had to choose a psi here, right? We had to choose this psi. And what role could this psi possibly play? It seems so arbitrary. Where does this come from? What is its role? How do we know what psi to choose? And this is a highly non-trivial question because there is so much choice. See? But how to choose psi? Could it be that the choice of psi doesn't matter? That the predictions come out the same no matter what we choose for psi? No. No. It's super important. The choice matters. The choice of psi is non-trivial because, first of all, it's non-trivial because psi has infinitely many components. That looks like bad news because it means we have to make an infinite amount of choices just to be able to make a prediction here. And secondly, the choice of psi matters. The choice of psi influences, in fact determines, influences, no, I should really say determines because that's what it is, it's much stronger. The choice of psi determines all predictions. From x bar of t to p bar of t, all of the f bar of t. The psi is in the calculation of these scalars, super importantly, totally determined by what we choose for psi. Mathematically speaking, the question is, in which direction in C infinity should psi point? You see, psi is a vector, a column vector with infinitely many coefficients. It is therefore an element of an infinite dimensional complex vector space. And the choice of psi is the choice of a vector, and it can point in any one of those infinitely many directions. How do we know in which direction it ought to point? Now, we should ask, why do we even have that choice? How come we have a choice here? Having gone through the effort of solving the equations of motion, solving the canonical commutation relations and hermeticity condition, shouldn't we have solved the problem? Why do we still have any choice to make? Actually, let's think back to classical mechanics. If you solve the equations of motion, the differential equation of motion, in classical mechanics, then you still can't make predictions. You still have to make a choice, even in classical mechanics. And the reason is that in classical mechanics, you have to choose initial conditions. The initial conditions determine which solution of the differential equations you get, and therefore all of your predictions. Now let's look at our situation here with the psi. The psi totally influences all our predictions, obviously, right? Because the psi totally determines what the x bar of t, p bar of t, etc. are. But remember that the psi is one choice that we get to make. It is a time-independent choice. All of the time dependence is in the solution of the differential equations. The choice of psi is a one-time choice. The choice of psi is the choice of initial conditions in quantum mechanics. So what we have is that in quantum mechanics, the choice of psi is the choice of initial conditions. I think that's worth highlighting. Such a pity that my handwriting is so lousy here, because this is a very important statement. In quantum mechanics, the choice of this vector psi that helps us to go from the matrix valued functions of time to the number valued prediction function of time, this choice of vector is the choice of initial conditions in quantum mechanics. Because if we choose psi, then we are choosing clearly what the prediction is for x bar of t, even at the initial time. And we're also choosing what the prediction is for p bar of t, even at the initial time, where we set the initial conditions, right? So choosing psi is determining what the prediction is, even at the initial time, which is to say, it's determining what we set the initial condition to be at the initial time. And then the time dependence of the matrix valued functions, that carries those initial conditions then further. Okay, so in quantum mechanics, the choice of psi is the choice of initial conditions. And it is a choice of direction in the complex vector space. Let's make some remarks now. One remark is that without restricting generality, we can choose the length of psi to be 1. So let me write it in a separate line. So we can choose 1 equal psi, which is the sum n equal 1 to infinity of psi star n psi n. We can choose this, which is to say that as far as the initial conditions are concerned, only the direction in which this vector points in this infinite dimensional complex vector space matters. The length of the vector doesn't matter. And that's because, well, we could also choose these vectors to all have length 27. We could absorb that 27 in units elsewhere in the calculations. So without restricting generality, we can and we will always choose our vectors here to be of our initial condition vectors, psi, to be of length 1. Now, next remark. We have infinitely many coefficients psi I to choose. And then we can predict infinitely many observables. Namely, we can then predict x bar of t, p bar of t, h bar of t, things like L, the angular momentum components of t, and indeed any f bar of t. So it seems this is fair enough. We can choose infinitely many coefficients for psi. In fact, we have to choose infinitely many coefficients for psi because it's a column vector with infinitely many entries. So we get to choose infinitely many numbers to specify the initial conditions. And then we can predict infinitely many numbers too. And even their time dependence, right? That's the whole point. So it would seem fair enough. Okay, infinitely many initial conditions, infinitely many predictions can be made. But, however, something is odd. Something seems odd. And what is that? Namely, in classical mechanics, we needed how many initial conditions? Two initial conditions, not infinitely many, but two initial conditions. We needed only two initial conditions. We needed x of t naught and p of t naught. And then we were able to predict from that we could predict by solving the equations of motion, we could predict x of t and p of t and h of t and all of the Li of t, all of the angular momenta, and indeed all of the f of t. How? Well, you see, in classical mechanics, if you can predict the position, then you can predict the momentum, then you can predict any polynomial of the position and the momentum. Obviously, right? So for example, if you can predict what the value is of the position, let's say x, well, then you can predict what the value is of the position squared. If you can predict the value for x and for p, then you can also predict the value for x squared p x squared minus 7p to the third, right? Because you know how to predict each x and p in there. So in classical mechanics, it was kind of trivial, right? You had to put two initial conditions, and then you could predict all of those things. Why would it not be the same in quantum mechanics? Why do we have infinitely many predictions? Why do we have infinitely many initial conditions? Do we really have that the situation is fair, as we just discussed? Because remember, it seemed fair. We have infinitely many coefficients in quantum mechanics, infinitely many psi to choose. But we said, fair enough, because we can make infinitely many predictions too. We can predict the x bar, the p bar, and things like any polynomials, right? Any polynomials in x and p. So we can predict, for example, x, we can also predict x squared bar, and we can predict x p to the 6th bar. But then let's remember, in classical mechanics, these were not separate predictions, right? Because in classical mechanics, if you can predict x, you can predict x squared. And if you can predict p, you can predict p squared. p to the 6, right? There's nothing extra. So it would seem that the whole thing collapses here. If only you can predict x bar and p bar, we can predict all of the other things too. No. There is a reason why in quantum mechanics we get to choose infinitely many initial conditions psi, when in classical mechanics we only choose 2 initial conditions. The reason is that in classical mechanics there really are only 2 things to predict: the x of t and the p of t, and then any polynomial of the x and the p can be predicted from what the x and the p are. Not in quantum mechanics. Why? The reason that we cannot in quantum mechanics, see, in quantum mechanics, x bar of t and x squared bar of t are, just as an example, are independent predictions. And similarly for p bar and p squared bar, or for any polynomial. You see, just because we know what x bar of t is and what p bar of t is, it doesn't mean that we can calculate, that we know what some polynomial of x and p bar is, what the prediction for that is. How do we see that? Why can I claim such an outrageous thing here? Well, why? Let's check. My claim is that if I take the prediction for x bar and I square it, then this is generally not the same as if I took the variable, the observable x, and squared it and then took the bar of it. The prediction for x squared is not the squared prediction for x in quantum mechanics. So, proof. Let's calculate these things. What is it? Well, x bar of t squared is what? Well, we have the sum n m, and then we have psi star n, and then we have x hat of t with matrix elements n and m, and then we have psi m, and that thing squared, right? Okay, now let's compare that with x squared of t, or actually I should write it more cleanly like this: x of t squared, and then we take the bar of that. What is this? Well, this is equal to sum over r s psi star r, and then the square of the observable here, that's the matrix x hat of t r v, and then again the matrix, square it, vs of t. Oh, why did I write it like this? Okay, and then it's vs, no, of t, and then vs, and then psi s. Okay, that's the prediction for x squared. And you see, those two expressions are generally not the same. There is no reason why they would be the same. The scalar product of a matrix squared is not the same as the matrix squared and then taking the scalar product. There's just generally no reason for them to be the same. In general, in quantum mechanics, they aren't. But what does that mean? So in QM, we generally have that if we take some observable and take its prediction value and we square that, then this is generally not the same as if we took the observable, squared it, and then take the prediction value of that. That's the same calculation as we just did for the position variable, right? We can do it for any thing in quantum mechanics because they're all matrix valued. For them, it's all works by the same way. So we have that these predictions for an observable are not the same. If you take a power, it doesn't even have to be the second power, it could be any power, right? That the power of a prediction is not the prediction of the power of any observable. That is weird. In classical mechanics, if you predict that the position of the ball is at the location 5.3 meters, then you know that the prediction for the square of the position is 5.3 meters squared. But here we have that this is not the case. How can that be? How can a theory make predictions of this weird kind? This does occur. It does occur in statistics. You see, what we are deriving here is that the predictions of quantum mechanics are statistical or stochastical. Let's say statistical. Namely, let's look at what why? Well, consider, for example, the difference for the position observable here between the two ways of calculating this. Consider, for example, on one hand, we have x of t squared, and then we make a prediction for it. And then let's say we consider how that differs, by how much that differs from taking the position, calculating the prediction for it, and then squaring that, right? We just said that in quantum mechanics, those two quantities aren't the same. And in statistics, when you have that your predictions are not sharp, when you're not so sure about what the outcome is, for example, you throw a ball, but you don't have full control over how you throw it, well, then you can predict the position of where the ball will hit the ground, but it's a probability distribution that you're going to get. And the prediction for the position of the landing of the ball squared is not the same as the prediction for the square of the positions where it lands. Right? So if you take the average of the squared predictions for the position, that's not the same as the square of the predicted positions. This quantity in statistics is, of course, known. It is the variance in x squared. Okay? So the fact that in quantum mechanics, powers of a prediction are not the predictions of the power matches beautifully with what we have in statistics. Because this is true not just for the second power, and it's, yeah. This means that we should expect that quantum mechanics makes predictions for expectation values but these are generally not sharp. Their expectation values, there are generally uncertainties or variances. And beautifully, quantum mechanics tells us not only, or allows us to calculate, but let's just say tells us not only how to calculate the prediction of an observable f bar of t. No, quantum mechanics also allows us to calculate how unsharp that prediction is, how much the variance or standard deviation in that prediction is. Namely, it allows us also to calculate what is f squared of t bar. And therefore, the variance delta f squared, which is, as we just discussed, f squared of t bar minus f of t bar squared. So quantum mechanics predicts what the expectation value, what the mean value of the outcome of a measurement is going to be, any measurement is going to be, but it also predicts the uncertainty in that prediction, and not just the uncertainty, but also all the other higher moments. Right? We can also calculate the expectation value for f to the third power, f to the fourth power, f to the fifth power, and so on. And there is, in fact, a whole discipline that is concerning how to get the full probability distribution from just the moments. Anyway, we will pick up from here next time. Until Friday then.